You step outside at night. The Milky Way stretches across the sky as a pale strip of countless stars. You are looking along the disk of our galaxy, through billions of suns at different distances. Between them lie clouds of gas and dust that hide what's behind. Somewhere in that direction, a massive star is reaching the end of its life. Soon, gravity will take over completely. Tonight, we ask a simple question with a long answer. We choose this one star and stay with it. It is massive, much more massive than the sun that warms our days. For a long time, it has fused the simplest element in its core into a heavier one. That first stage has ended. Inside, the central fire has changed. The star has stepped through many stages of fusion and has reached the late part of its life. From the outside, your eyes would not notice this change. The light still looks steady. The surface still drifts with quiet ripples. But deep inside, in the center where the pressure is greatest, the star is running out of ways to keep its balance. A star glows because it holds itself up. Gravity pulls inward on every layer. The pressure and heat at the center push outward. The outward push comes from fusion. When very light nuclei join to form heavier ones, they release energy. That energy shows up as heat and light, and as the pressure that holds gravity back. In a massive star, the center is dense and hot enough to support a ladder of fusion stages. Each stage makes new fuel for the layer above it, and new ash for the layer below. Over time, the core changes its composition as it consumes its fuel and creates heavier elements. In its early life, this star fused hydrogen into helium. The helium built up in the center, while hydrogen fusion moved into a shell outside the center. As the core filled with helium and heated further, helium fusion began. Helium nuclei joined to make carbon and oxygen. The star adjusted, finding a new balance. Gravity drew in. Fusion pushed out. The surface brightened and dimmed a little as the interior shifted, but the star kept its shape and stayed whole. The heavier core meant higher pressure. Higher pressure meant higher temperature. That temperature allowed new reactions. Carbon fusion started once helium fuel in the center became scarce. Carbon nuclei collided and merged, forming neon, sodium, and magnesium. The details depend on exact temperature and density. In a massive star like this one, the central environment moves quickly through the thresholds that open new fusion pathways. Each step begins when the conditions allow it and ends when the fuel runs down. After carbon, neon burning began. In this stage, high-energy photons inside the core kick out particles from neon, which then combine with other nuclei. The process makes oxygen and magnesium and helps prepare the core for the next step. The timescales change. Hydrogen fusion can last many millions of years. Helium fusion lasts fewer millions. Carbon burning is shorter. Neon burning is shorter still. The later stages pass like brief seasons compared to the long early ones. But even these short seasons are slow when seen through human days. The star does not hurry. It follows physics with quiet patience. When oxygen burning starts, the core has grown still hotter and denser. Oxygen nuclei fuse into silicon, sulfur, and other elements near that region of the periodic table. The reactions release energy that supports the star against gravity. Again, the star finds a new balance, but this time the balance is more delicate. The core is now a tight sphere of very dense matter. Heat leaks out in the form of neutrinos, tiny particles that pass almost unhindered through ordinary matter. In these conditions, neutrino cooling is very strong. It drains energy from the core faster than light alone could carry it away. To keep up, fusion must proceed more quickly. The star responds by fusing oxygen faster and heating further. You can picture the interior as layers, with the center at the highest pressure and temperature. Nearest the center sits the current fusion ash. Around that sits a shell where the previous fuel still burns. Surrounding shells host earlier stages: a shell where helium still fuses, a shell where hydrogen still fuses. Each shell burns at its own rate, feeding energy into the whole star. The outer layers expand and contract as the deeper layers change. The light you see is the sum of all these processes, smoothed by distance and time. But inside, the structure becomes more complex as the star ages. The core now approaches the last common stage of fusion in massive stars. Silicon burning is the final major step. It is not like early fusion, which brings two small nuclei together cleanly. Silicon burning is a network of reactions. At the core temperatures now, photons can knock out small particles from heavy nuclei. Those particles, such as alpha particles, quickly attach to other nuclei. The matter in the core shuffles into a set of nuclei with the highest binding energy per particle. Iron and elements nearby in mass become favored. The result is an iron-rich core. Iron here is not fuel. Joining iron nuclei does not release energy in the way earlier stages did. Splitting iron does not help either. The curve of nuclear binding peaks near iron, so the star reaches a point where fusion can no longer give the pressure needed to hold gravity back. During silicon burning, the star shines with great power. It loses energy through neutrinos at a rate that dwarfs the energy it radiates as light at the surface. The interior must work very hard to maintain balance. Yet, to an outside observer, the star still appears calm. The surface temperature and brightness may shift, but not wildly. Deep within, the silicon burning core turns matter into iron, like a factory running out its final day of production. The core grows in mass as iron ash piles up, and the active silicon burning region moves outward as shells ignite in sequence. The physics of the core pressures now includes electron degeneracy. The matter is so dense that electrons fill the lowest available energy states. This gives a quantum pressure that does not depend on temperature in the same way as ordinary gas pressure. Electron degeneracy can support a core up to a point. As the iron core grows, it approaches a critical mass. Around this mass, the electron degeneracy pressure can no longer support the core against gravity. The exact threshold depends on the composition and conditions, but it is around 1.5 times the mass of the Sun. As silicon burning deposits more iron, the core moves toward that limit. While the iron core builds, several things accelerate its fate. Neutrino losses increase with temperature, sapping energy. At very high temperatures, energetic photons begin to disassemble iron nuclei into helium nuclei and free neutrons and protons. This is called photodisintegration. It absorbs energy, further reducing pressure. Also, electrons in the dense core are captured by protons in nuclei, making neutrons and emitting neutrinos. Electron capture removes electrons that were contributing to the degeneracy pressure, weakening the support. The core thereby loses an important pressure source just when gravity demands more. It helps to slow down and trace cause and effect. The star fused elements to provide pressure against gravity. Each new stage produced a heavier core and required higher temperature to ignite the next fuel. Late in life, radiation and neutrino cooling increase. The core must heat more to compensate. Silicon burning makes iron, which cannot release fusion energy to provide new pressure. As iron accumulates, the core's effective support becomes mainly electron degeneracy. As mass grows, this support approaches its limit. Electron capture and photodisintegration reduce pressure further. The system has many feedbacks that push it toward instability. The shells above the core still burn. Helium and hydrogen shells contribute energy that supports the outer layers. Those layers may puff out and produce a strong stellar wind. The wind carries off mass from the surface, but the fate of the star now rides on the core. The outer layers are tied to what happens deep within. If the core cannot hold itself up, the entire star will respond. We can pause and consider time. The early life of this massive star has taken many millions of years. The late stages have passed more quickly. Carbon burning might last only thousands of years. Neon and oxygen burning go by in even shorter spans. Silicon burning is the briefest, measured in about a day in many cases. The core now approaches the end of that short interval. In that time, the mass of the iron core has climbed. The temperature sits at a high value. The density has risen to a level where matter is packed tightly. Neutrinos stream out, carrying energy away. The star does not negotiate with these processes. It simply follows from the conditions. Physics describes what can happen. If the core mass crosses the limit where electron degeneracy fails, gravity takes over. The collapse starts. But we are not there yet. We are just short of that moment. The silicon ashes are still settling into the center. The capture of electrons is increasing. The core is very close to its maximum supportable mass. Let us zoom inward with care. At the very center, the iron core is almost isothermal compared to the steep gradients around it. The core tries to remain stable, but it must transport energy. Neutrinos carry energy away easily in this density and temperature regime. They stream out without depositing much heat in the surrounding layers. The core cannot rely on radiation to move energy outward effectively. Thermal energy leaks by neutrino emission. This leak makes the core cool locally, which increases its tendency to contract. As it contracts, it heats. Heating speeds up electron capture and photodisintegration once the threshold is crossed. This interplay defines the tipping point. Just above the iron core lies the silicon burning shell. Here, silicon and related nuclei continue to transform. The shell is hot and vigorous. Its burning provides little direct support to the core, but piles more iron onto it. The growth is not uniform. Convection may transport material and heat in the shells. The star seeks equilibrium, but the timescales are too short for a perfect adjustment. The silicon burning region may flash in episodes, each episode adding to the iron core. Farther out, the oxygen and neon shells contribute their own fusion. Even farther out, the helium and hydrogen shells continue. These shells release energy that puffs up the envelope and can drive mass loss. Strong winds peel off the outer layers. Dust may form in the cooler extended atmosphere and be carried away. The star leaves a trail of enriched material in the interstellar medium. That material will seed future generations of stars and planets. This is one way heavy elements spread through a galaxy. It is a slow flow measured over the star's late life, not a sudden change. Now zoom out a little. Stars like this are not rare in a large spiral galaxy. They live in the arms where gas is dense. They form in clusters. Many of them are in binary systems. Some will end their lives as neutron stars. The most massive will form black holes. Our chosen star is on the border between these outcomes, but its mass and core history point toward a black hole. Its iron core is large. Its envelope mass is still significant despite winds. When the collapse begins, the shock will try to move outward through those layers, and its success will depend on complex physics. Whether the envelope is ejected fully or partially, the remnant will be compact. With a high enough mass at the center, the remnant will be a black hole. We will follow that path soon. For now, we remain with the core as it approaches instability. At these temperatures, nuclear statistical equilibrium becomes a useful concept. The matter in the core tends to distribute among nuclei according to conditions of temperature and density. The composition drifts toward iron group elements. Small changes in temperature can shift the balance in these conditions. Photodisintegration starts nibbling at the largest nuclei, producing helium nuclei and free nucleons. This process consumes energy. An energy sink in the core is dangerous for stability. It makes the pressure lower for the same density, encouraging contraction. Contraction raises temperature, which makes photodisintegration stronger. This is another feedback cycle that points toward collapse. Electron capture occurs when electrons are pressed so tightly that merging with protons becomes energetically favorable. In dense cores, electrons have high energies because their allowed quantum states are filled up to a high level. If an electron meets a proton in a nucleus and capture is allowed, a neutron is formed and a neutrino is emitted. That neutrino escapes, removing energy. Removing electrons also lowers degeneracy pressure. With fewer electrons to resist compression, gravity wins more easily. As capture rates rise, the core's pressure support declines faster and faster. The physics of the limit on electron degeneracy support can be expressed with precise relations, but we can speak plainly. There is a maximum mass that a non-rotating, non-thermal, electron-supported core can hold up. If the core mass stays below that value, the star can avoid immediate collapse. If it grows beyond, the support fails. The iron core uses electron degeneracy as its last standing pressure against gravity. Because the core is so hot, thermal pressure also contributes. But neutrino cooling erodes thermal energy rapidly. So the balance leans hard on degeneracy. Neutrinos deserve another quiet look. In earlier fusion stages, neutrinos are produced but play a small role in energy flow. In these late stages, neutrinos dominate the energy loss. They do not interact strongly with normal matter. They fly through the dense layers and escape. The core becomes a powerful neutrino source, though no human sense can detect this without instruments. The star's interior brightness in neutrinos is beyond any light it has ever emitted. That brightness robs the core of the energy that could help sustain pressure and maintain a gentle state. The core tightens. What does the surface do while all this happens? It brightens according to the increased energy from the shells, and it may vary on timescales tied to the convection and instability of those shells. Winds strip mass from the star. The spectrum shows signatures of heavy elements mixed into the outer layers by convection and prior mass loss. The star might look like a blue supergiant or a red supergiant, depending on its mass, metallicity, and wind history. In our case, the star has shed some mass and maintains a hot surface. But the exact surface appearance does not change the central fact. The core is reaching the end of fusion support. It is useful to think of the star as a system seeking balance. Gravity considers only mass and distance. Pressure considers temperature, particle populations, and their quantum states. Fusion is the mechanism that maintains temperature in the center. As long as fusion reactions release energy faster than cooling processes remove it, and as long as that energy translates into pressure, the star can balance gravity. Silicon burning cannot extend this balance for long. It is too short and ends in a pile of iron. When that happens, the core's temperature and density are such that energy removal and pressure loss happen faster than new support can be built. In the last hours of silicon burning, the core may be convective. Convection transports heat and mixes composition, but the mixing length is limited by the short time. The distribution of silicon and iron can be irregular on small scales. This can influence where the collapse starts first. But from the point of view of the entire core, these details only set the exact second of failure, not the general outcome. It is as if the core holds its breath against gravity and tries to keep the last bit of support, while iron ash piles higher. Let us trace the path of individual particles in the core. Photons bounce and scatter, but in the core they are absorbed and re-emitted many times. Their energies are high. Some become part of photodisintegration events that break nuclei. Electrons move as a degenerate sea. They cannot all drop to lower energy states because those are already filled. Protons and neutrons remain bound in nuclei but feel the changing balance as temperature and density rise. When an electron is captured, a neutrino flies out. Each such event changes the composition and the pressure. The speed of these microphysical events increases as conditions worsen. We might wonder what sets the precise moment when balance fails. It is not a single universal number because rotation, composition, and temperature make small differences. But the logic is simple. The mass of the iron core grows. Electron capture reduces pressure support. Photodisintegration consumes heat. Neutrinos carry energy away. The temperature and density cross thresholds that make these effects strong. When the total pressure that can be raised by the core is less than what gravity demands, collapse begins. It starts at the center and moves outward as layers lose support from the layers beneath. Before this moment, the star still keeps all its material gravitationally bound and intact. No shock has formed yet. There is no outward blast. The outer shells continue their fusion. The envelope continues to leak mass through winds. The star looks to an observer like a bright, steady point. Its apparent calm hides the internal race between support and loss. To describe it is to watch slow preparation for a rapid event. We can imagine a timescale shrinking inside the star. Hydrogen burning lasted many millions of years. Helium burning lasted a fraction of that. Carbon burning lasted thousands of years. Neon and oxygen burning lasted months to years, then months to weeks. Silicon burning lasts about a day. Inside this final day, the core tightens hour by hour. Electron capture rates climb. Neutrino luminosity surges. Pressure margin thins. In the last minutes, the rate of change steepens as feedback loops tip more reactions into action. On the edge of the core, where silicon still burns, convection tries to deliver fresh fuel to hot regions. This sustains fusion a little longer, but the extra iron thus produced is exactly what pushes the core toward failure. The burning shell does not know that it is undermining the last supports. It only follows the conditions set by temperature and density. The shell acts as a conveyor, moving iron inward by deposition and by the slow settle of heavy nuclei. Under gravity, heavy nuclei sink toward the center. Each small addition matters. The structural profile of the star at this stage shows a dense, iron-rich core of a size comparable to a small planet, yet holding mass similar to the Sun or more. Above it are shells of silicon, oxygen, neon, carbon, helium, and hydrogen. The transitions between shells are not infinitely sharp. They are smeared by mixing and prior burning fronts. The pressure gradient is steep, and the density drops rapidly outward. The entire star is still huge compared to the core. If you could slice the star and look at it, the core would seem small, but in terms of gravity and fate, it is everything. The chemistry inside the core is not chemistry as we know it. At these temperatures, atoms are fully ionized. Nuclei and electrons move in a high-energy plasma. The nuclear reactions are set by cross-sections and available energies. The electrostatic repulsion between nuclei, which prevents fusion at low temperatures, is overcome by the high thermal energy and by quantum tunneling. As we move to heavier nuclei, the required temperatures and densities increase. That is why late stages are compressed into short times. The star must climb higher in temperature for smaller gains in energy release, and the gains diminish as iron approaches. If the star had been less massive, it might end its life differently. The core might stop at a stable form supported by electron degeneracy and shed its envelope gently. It would become a white dwarf. But in our star, the core mass and temperature drive it beyond that outcome. The core tries to be an electron-supported object and fails. Soon it will become a neutron-supported object for a moment, and then it may go further. The details will depend on how much mass continues to fall inward after the core bounces. But that is ahead of us. We remain at the threshold. There is a quiet connection here to the future black hole. A black hole is not a material object in the usual sense. It is a region where gravity curves space-time so strongly that not even light can escape. For our star to form such an object, the collapsing core must compress beyond the limit where even neutron pressure can hold it up. That requires sufficient mass and continuing infall. The current state of the core, with its iron buildup and loss of support, is the doorway to that future. Crossing the doorway begins with core collapse. The collapse will happen in a handful of heartbeats of the star, but the preparation has taken all of stellar life. You look again at the point of light. It feels steady and plain. No sign flashes to mark the physics inside. The distance hides details. Space lets the light travel without telling its story. Yet the story is there. The last minutes of silicon burning are drawing to a close. The core's mass is near its limit. The heat at the center encourages photodisintegration. Electrons are being captured. Neutrinos are pouring out. The core is about to lose the last margin of pressure that keeps gravity in check. We can name the threshold clearly. When the iron core can no longer supply pressure through its electrons and residual heat, it cannot stand against gravity. It starts to contract. The contraction feeds the very processes that reduce pressure. The contraction becomes a collapse. The collapse speeds up, becoming almost free fall in the inner region. In the next moments, the density will rise to nuclear values. The protons and electrons will be forced together in the crush, making neutrons in large numbers. A shock will form when the inner core rebounds, then it will stall, then it will need neutrino heating and complex flows to revive. The outer layers will feel the shock and begin to move. Light will not show the first stages. Neutrinos will escape first. But that is the next chapter. For now, the star stands on the cliff. The silicon flame fades at the exact center because no new fusion there can help. The iron assembly is complete. The electron sea is thinning by capture. The photon field is disassembling nuclei at the top of the energy distribution. The core pressure is just less than gravity now, or will be within moments. The layers above continue their work, unaware in any human sense, running the code of physics they have run for all this time. Soon their fate will reach them from below. The iron core faces gravity with less pressure than it needs. Electron capture has removed many of the electrons that once helped push back. High-energy photons keep breaking iron nuclei into lighter pieces, and that process absorbs heat. Both effects drain the core of support. Gravity notices only mass and distance, so it does not slow or wait. It keeps pulling. The moment arrives when the inward pull exceeds what the core can resist. Then the center begins to sink. At first, the motion is slow compared to what will follow. The inner part of the core loses pressure and starts to contract. Contraction heats the matter, which would normally push back, but the heat is consumed by breaking nuclei apart and by making more neutrinos through electron capture. Those neutrinos carry energy away almost without interacting. The core cannot recover the lost pressure. The collapse speeds up. The time scale shrinks. In less than a second, the inner core moves from a dense but familiar state to one that no ordinary matter experiences outside of such a star. The motion is nearly free fall. Layers above press down and add momentum. The central density rises rapidly. Photodisintegration eats thermal energy as fast as the temperature rises. Electron capture continues, turning protons into neutrons and sending out more neutrinos. The population of electrons that once supported the core falls. Gravity pushes harder as the inner mass grows more concentrated. Nothing in the core can stop to rearrange slowly. There is no time. As the collapse reaches its steepest phase, the inner core approaches densities like the density of atomic nuclei. In that regime, neutrons are packed almost shoulder to shoulder. The strong force resists further compression when nucleons are forced too close. The inner core feels this resistance as an almost solid behavior, though the matter is not a solid in any usual sense. The inward motion suddenly meets a wall of stiffness at nuclear density. The inner core decelerates sharply. It rebounds. This rebound is not a bounce that returns the inner core to its previous size. It is a brief reversal that sends a pressure wave outward through the still infalling outer core. That pressure wave strengthens into a shock front, a thin region where temperature, density, and pressure jump. The shock rushes outward into material that is still falling inward. That material is moving fast and carries large kinetic energy. The shock must plow through it and convert some of that energy into heat and pressure. The newly formed shock consumes energy in two costly ways. First, it must break heavy nuclei into lighter particles as it passes. Photodisintegration at the shock front takes energy that would otherwise help the shock push ahead. Second, the hot matter behind the shock emits neutrinos that leave, removing more energy. The outward front slows and risks stalling. It travels a small distance from the center and then loses strength. The star is not saved yet. During these same moments, the core emits an enormous burst of neutrinos. The density inside is so high and the temperature so extreme that neutrino production skyrockets. At first, neutrinos stream freely from regions where matter is not quite dense enough to trap them. Deeper in, even neutrinos begin to scatter and exchange energy with matter. The inner tens of kilometers become a region where neutrinos are at least partly in contact with matter before they escape. Over a short time, a flood of neutrinos carries away more energy than the star has radiated in light over its entire life. This happens mostly inside the star and is invisible to ordinary sight. It is the main way the core loses energy and changes state during the crucial seconds. The shock that formed at bounce needs help. Alone, it would fade. Neutrinos provide that help. They stream from the hot inner core and deposit a small fraction of their energy in a layer just behind the shock. This heating is weak compared to the total neutrino energy, yet it matters. It reheats matter that had cooled, increases pressure, and can revive the shock. Convection in that layer, the rising of hotter material, and the sinking of cooler material helps distribute the heat and makes the flow more efficient. The stalled shock begins to move again. It gains speed. It pushes through infalling layers one after another. As the shock gains strength, it starts to unbind the outer envelope of the star. The front crosses shells of silicon, oxygen, neon, and carbon. It moves into helium and hydrogen farther out. Each region has its own density and composition. Each offers its own resistance. The shock compresses, heats, and accelerates matter outward. Nuclear reactions occur in the wake of the shock, making new elements in brief surges where temperatures and densities pass through the right values. The outer layers begin to feel an outward push that exceeds gravity. They accelerate away from the center. After a brief delay from the instant of core bounce, the shock has enough energy to escape the inner regions. A supernova explosion begins to take shape. The surface is still far away. Light from the shock's emergence will reach the outside only after more time has passed, but the envelope has started to move. Deep inside, neutrinos keep pouring out. They continue to heat the region behind the shock. They help drive matter into an organized outflow. As the shock runs outward, some of the innermost material briefly tries to fall back. The fate of that material depends on the total energy budget. In a less massive star, the outward push and inner pressure can leave behind a neutron star. In our more massive case, the core mass is larger, and the continuing infall is stronger. The inner object that formed at bounce is a hot, dense sphere of neutrons and other particles. For a short time, it holds up under neutron degeneracy pressure and thermal pressure. But material from above keeps falling in. If the central mass grows beyond the maximum that neutron pressure can support, even this last support fails. The transition to a black hole happens when the matter within a shrinking region is confined inside a boundary from which light cannot escape. This boundary is the event horizon. It is not a surface made of matter. It does not have texture or shape in the way a physical object does. It is a geometric boundary in space-time, defined by the paths that light and matter can take. Outside the boundary, some paths lead outward to infinity. Inside the boundary, all possible paths lead farther inward. Once the collapsing core crosses this limit, no signal from inside can reach the outside. During the milliseconds when the central mass crosses its critical value, the space-time around it changes in a definite way. For a distant observer, processes near the boundary appear to slow as light struggles to climb out of a deep gravitational well. For an observer falling with the matter, the crossing is uneventful in the sense that no special force announces the horizon itself. The matter continues inward. The horizon forms and grows as more mass passes within it. At nearly the same time, the outgoing shock has already committed the outer layers to their path. Those layers have kinetic energy set by the revived shock and by neutrino heating. They no longer depend on what happens at the center. They will break free. The outer parts of the star blow apart. They carry away elements forged in the star's life and in the brief nuclear reactions induced by the shock. The supernova becomes visible when the shock reaches the surface, and the stellar envelope is suddenly heated and expanded. That light, when it arrives to a viewer far away, will tell the story of a catastrophic change. But the central object will not speak in light. The neutrino flood ends a short time after the core collapses into a black hole. Once the horizon encloses the region where neutrinos were being created and scattered, they can no longer escape from inside. The neutrino signal, which had risen to a very high rate, shuts off almost abruptly. This abrupt end is a sign of horizon formation. It marks the moment the inner region becomes causally disconnected from the outside world. If detectors were watching, they would register a burst and then silence. What remains at the center is a black hole. Its properties are simple to name and profound in consequence. It has mass, which determines the size of the horizon. The more mass it has, the larger the horizon radius. It has spin because the core had angular momentum, and that angular momentum cannot simply disappear. It may have electric charge in principle, but matter on these scales is overall neutral, so the charge is negligible. The black hole has no surface. There is no place you can stand. There is only the horizon, which is a place defined by the geometry of light paths, and there is the warping of space-time itself. Outside the horizon, the curvature of space-time is smooth. If you are far away, you feel only the gravity that depends on mass and spin. The field is not sharp or jagged. It falls off with distance. Orbits that were stable around the original star may now be altered depending on how much mass was lost in the explosion and how much remains. Some outer material is unbound and escapes. Some inner material may remain gravitationally bound and later fall back. If there is a companion star, the system may survive and continue as a binary, now with a compact object in place of the original star. We do not see a black hole directly because it does not emit light of its own in the way ordinary objects do. Instead, we detect its effects on nearby matter and light. If gas orbits close to the black hole, it can form a disk as collisions, and friction force the gas into a thin, hot structure. The inner parts of the disk shine in high-energy light because gas there heats to very high temperatures. This radiation can be fierce, but it is emitted by the gas outside the horizon, not by the black hole itself. We also observe the motions of stars and gas under strong gravity. A star in a tight orbit that moves too fast for any visible mass to account for, it suggests an unseen compact mass, which is a good sign of a black hole. We can pause here and follow the rotation inherited from the collapsing core. The original star spun, even if slowly. When an object shrinks, its spin rate tends to increase because angular momentum is conserved. The inner core that collapsed carried this angular momentum inward. The black hole that forms keeps that spin. A spinning black hole affects space-time differently than a non-spinning one. It drags the nearby fabric of space-time around with it. This effect is called frame dragging. Frame dragging means that close to a spinning black hole, space and time are not simply curved inward. They are also twisted around the axis of spin. An object that tries to stay at rest relative to very distant stars cannot do so arbitrarily close to the hole. The dragged space-time compels it to move in the direction of the spin. Surrounding the horizon, in the case of a spinning black hole, is a region where no stationary path is possible. This region is called the ergosphere. It lies outside the horizon. Within the ergosphere, every path must rotate with the hole in some sense, though some paths still allow escape to the larger universe. The ergosphere has a clear boundary, defined by where the dragged space-time becomes so strong that the time direction for a stationary observer would point inward rather than forward. That is not allowed for physical observers, so nothing can remain stationary there. This is a feature of the geometry. It has practical consequences. Processes inside the ergosphere can, in principle, extract rotational energy from the spinning hole by sending part of a system into the hole on a path that reduces the hole's spin and allows the other part to fly out with more energy than it had before. In nature, magnetic fields and plasma flows may tap this rotational energy and power large, collimated outflows from near the black hole. But those are developments for later. For now, the key is that rotation changes the nearby space-time and influences how matter moves and how energy flows. Return to the moment just after formation. The explosion has cast off the outer layers of the star. The shock has left the inner regions. The black hole has formed and enclosed the inner core. Around it remains some chaotic debris. Some of this material continues outward and escapes. Some of it lacks sufficient energy and will fall back. As it falls, it can form an accretion flow. If the material has even a little angular momentum, it cannot fall straight in. It circles. Collisions and magnetic forces redistributes angular momentum, allowing some gas to move inward while other gas moves outward. The inward gas heats as it spirals closer to the horizon and radiates energy before crossing it. The newborn black hole does not have a surface, so there is no sudden impact as matter reaches it, but there is a last stable orbit outside the horizon. Inside that orbit, circular paths are not possible. Matter that crosses that radius plunges inward quickly. The location of the last stable orbit depends on the spin of the black hole and on whether the orbit moves with or against the spin. For orbits aligned with the spin, the last stable circle is closer to the horizon. For orbits against the spin, it is farther out. This difference is a direct expression of how rotation changes the geometry around the hole. The horizon itself is a special surface in mathematical description, but locally, it does not exert a mechanical force. The tidal gravity near the horizon can be strong, depending on the mass. For a small black hole, the gradient in the gravitational field across small distances can be intense. For a larger black hole, the gradient at the horizon can be gentler. In every case, once matter crosses the horizon, its future is sealed. It adds to the mass and spin of the hole and cannot send any message back to the outside world. How does a distant observer know that a horizon has formed, and not a different kind of compact object with a surface? One clue is the absence of any sign of a hard surface in the light from infalling matter. If there were a surface, matter would release additional energy when it struck. Another clue is the way time dilation affects signals from near the presumed horizon. Light emitted from close to a horizon is redshifted strongly and appears to take longer to arrive. The spectrum and timing of the light from accretion disks are consistent with a surface of no return, not with a radiating surface. Observations also show stars orbiting an unseen mass at speeds and distances that point to compactness beyond any known star. These lines of evidence together support the presence of horizons. We can consider what the black hole is not. It is not a hole in matter. It is not an empty cavity. It is a region where space-time is curved so strongly that all paths inside trend inward. The mass that fell in is still accounted for in the gravitational field felt outside. The simplicity of the exterior field is part of what makes black holes striking. If you know the mass and the spin, you can describe many aspects of how the hole will influence its surroundings. The external details of how the hole formed do not matter to the geometry once the horizon is there. The star's layers, their shapes, and the chain of fusion stages have all been reduced to a few global numbers that guide the flow of space-time. The supernova now expands. It carries the chemical record of the star's life into space. Elements produced in shells and in the shock-driven reactions move outward. As the ejecta cool, atoms form, then molecules, then dust grains in some places. A remnant of hot gas and magnetic fields grows and brightens in high-energy light. That remnant will evolve for a long time. It may run into neighboring clouds and trigger new star formation. It may mix with the interstellar medium and enrich it. The black hole at the center quietly adds to its mass, if any fallback reaches it. If the star had a companion, matter from the companion may feed the black hole later. If not, the black hole may drift in relative quiet, its presence marked only by its gravity. Rotation continues to matter. The spinning hole sets a preferred direction in space, its axis. Accretion flows align with that axis over time. Magnetic fields can wind up around the hole and the inner disk. The frame dragging near the horizon can twist these fields and help launch jets, narrow streams of plasma that shoot away from the system at high speeds. Such jets are not guaranteed in every system, but when conditions are right, they can carry energy and matter far from the hole. Even then, the horizon remains quiet in the sense that nothing crosses it and returns. All the action we can observe takes place outside. From our quiet vantage under the night, none of this appears as motion to the eye. The distances are too great. The timescales for the visible light show are longer than a human moment. But the essential part, the formation of the black hole, is over in a blink from the star's point of view. The collapse ran its course. The shock formed, faltered, and then succeeded with the help of neutrinos. The outer layers began their outward flight. The center crossed the boundary of no return and became a black hole. The spin that was carried inward now shapes the geometry around the horizon. There is a simple way to hold this picture. Gravity pulled, pressure failed. The core fell, rebounded at nuclear density, and sent out a shock. Neutrinos flooded, heated the stalled region, and helped drive the explosion. The star's outer layers left. The inner mass shrank until a horizon formed. The object that remains is small in size compared to the star, yet heavy. It has no surface, just a horizon. It has spin, which drags space-time nearby and creates an ergosphere. It waits to be fed by any matter that strays too close or that falls back from the explosion. The explosion has sent most of the stellar envelope outward. Some gas escapes, some slows and turns back. The gas that returns does not fall straight in. It carries angular momentum from the star. Even a small amount is enough to keep it from plunging directly to the horizon. The gas meets itself as it turns, collides, and sheds energy. It flattens into a broad, rotating flow. This is the beginning of an accretion disk. The disk takes shape near the black hole and extends outward into the thinner interior of the remnant. Gravity pulls inward. Rotation holds each ring of gas at a distance where its orbital motion balances the inward pull. But the gas is not solid. Neighboring rings rub. Magnetic fields thread the plasma and tie distant parts together. Tiny instabilities in the magnetized flow grow and stir the disk. The result is a slow transport of angular momentum outward and a slow drift of mass inward. This transport is continuous. Gas at one radius passes a little angular momentum to gas farther out. In exchange, it moves closer to the hole where orbits are faster. As it sinks, gravitational energy changes into heat. Collisions and magnetic turbulence turn orbital energy into thermal energy. The disk warms. The inner parts become very hot. They shine in high-energy light. Most of that light is not visible to the eye. It is in X-rays and ultraviolet. The X-rays tell us that gas near the hole reaches very high temperatures before it crosses the last orbit that can be stable. There is a special circle in the geometry around a black hole. It is the innermost stable circular orbit. Far from the hole, a small change in speed or position still allows a circular path. Closer in, circular orbits are still possible, but they are less forgiving. At the innermost stable circle, the balance is delicate. Inside that radius, no circular path can remain stable. A small inward push leads to a rapid plunge. The location of this orbit depends on spin. If the disk turns in the same direction as the hole, the innermost stable orbit lies closer to the horizon. If the disk turns against the spin, the innermost stable orbit is farther out. This difference reflects how rotation twists space-time near the hole. Gas in the disk slowly drifts inward until it approaches this last stable circle. There, friction and magnetic turbulence still act, but the timescale shortens. A small loss of angular momentum sends the gas across the boundary. Then, the motion changes character. The gas does not orbit much more. It falls inward quickly. It crosses the horizon in a very short proper time, which is the time measured by a clock moving with the gas. There is no surface to hit, and there is no flash at the horizon itself. The energy the gas can radiate mostly leaves before the plunge. Inside the last circle, little more escapes. The remaining energy and momentum go with the gas into the hole. A distant observer sees these events through the lens of gravity. Light from gas near the horizon loses energy as it climbs out of the strong field. Its frequency shifts downward. Time between successive wave peaks stretches. Processes near the horizon also appear to slow. A flash sent from the last orbit looks delayed and softened. A bright spot that skims the inner disk appears to circle and then fade as it nears the horizon. From far away, the infalling gas seems to take a very long time to disappear. Locally, for the gas and for any object that falls, the crossing happens quickly. Both views are true within their frames. Time and space are not the same for all observers near a strong gravitational field. The disk is not perfectly smooth. Clumps and spiral features form where magnetic turbulence and pressure variations grow. These clumps heat and cool as they move. They produce flicker in the X-rays. The rate and pattern of flicker carry information about the inner radii, the spin, and the way the disk transports angular momentum. In some systems, the disk also produces a wind. Thermal pressure and radiation pressure push gas away from the disk surface. This wind carries mass off and changes the rate at which the hole feeds. The mix of inflow and outflow depends on the supply of gas, the magnetic field strength, and the efficiency of cooling by radiation. The newborn black hole has strong frame dragging in its closed neighborhood. The rotating spacetime forces nearby matter to share some of the spin. The effect weakens with distance, but close in, it is important. The inner disk tends to align with the spin axis of the hole, even if the outer disk started tilted. Warps in the disk travel inward and settle. Over time, the disk and the black hole find a common plane near the center. This alignment helps organize the flows that launch along the axis. Magnetic fields tie the disk to the region close to the horizon. The fields thread the plasma as loops and open lines. Rotation winds them up. When these fields become strong enough, they can guide charged particles away from the disk and along the rotation axis. The result is a pair of collimated outflows called jets. In the most efficient cases, the fields tap rotational energy from the spacetime near the hole. The energy moves into the jets as electromagnetic energy and as kinetic energy of fast particles. Jets begin close to the hole but reach far beyond the disk. They carry plasma outward at speeds near the speed of light. The jet beams are narrow near the base. As they move outward, they interact with slower material in the remnant and in the interstellar medium. Shocks form where the jets meet resistance. Those shocks accelerate particles and cause them to radiate in radio and X-rays. The details of jet power vary with spin, magnetic field strength, and accretion rate. In the early period after birth, when fallback and disk feeding are vigorous, jets can be strong. Later, as the supply declines, the jets fade or switch to a weaker, intermittent mode. Tidal forces near the horizon deserve a clear account. Gravity changes with distance from the center. If an extended object falls in, the part closer to the hole feels a stronger pull than the part slightly farther away. This gradient stretches the object along the direction toward the center and squeezes it in the perpendicular directions. The strength of this effect depends on the mass of the black hole and on how close the object gets. For a small black hole, the gradient can be strong even outside the horizon. For a more massive one, the gradient at the horizon can be modest. In our case, the mass is a few times the mass of the Sun, so the gradient is strong near the horizon. A small compact object like a rock or a dead planet would be pulled into a long shape and shredded by internal stresses if it came too close. Gas does not resist in the same way and simply follows the flow. This stretching and squeezing has a signature in the disk. Matter that strays inward and becomes unstable does not fall as a single clump for long. Differential motion tears it into streams that spread around the hole. The streams heat as they collide with faster-moving gas behind them and slower-moving gas ahead of them. The heat adds to the radiation we observe. The exact pattern of brightening and dimming can show quasi-regular oscillations that hint at orbital periods near the last stable circle. Those periods encode the mass and spin indirectly. As time passes, the initial supply of fallback material dwindles. The disk thins. The heating rate falls. The X-ray brightness drops. The jets, if they formed, weaken. The black hole enters a quieter phase. If the exploded star had no companion, the whole now depends on chance encounters with clouds in the interstellar medium. These encounters are rare and usually provide only a small amount of gas. Feeding becomes intermittent and faint. The whole drifts through space with the velocity it inherited from the supernova's asymmetries and from its original orbit in the galaxy. If the star had a companion, a different path unfolds. The explosion might have unbound the pair, or it might have left them together in a new orbit. In a bound system, the companion may later expand as it evolves. Its outer layers can overflow the point where the black hole's gravity is stronger than the star's hold. Gas then streams toward the hole and forms a new disk. In such systems, the X-ray light can flare when the disk forms and dims when the supply pauses. These are called X-ray binaries. They show the same basic accretion physics on smaller scales and at different feeding rates. Our black hole may or may not have such a partner. If it does not, we imagine it as a quiet object now. Its mass has grown a little from fallback. Its spin has adjusted to the net angular momentum of what it swallowed. It keeps both mass and spin unless it later accretes more or merges with another compact object. The surroundings cool. The supernova remnant expands and thins. Eventually, it blends into the ambient gas of the galaxy. Only a faint shell or filamentary structure may mark the site, and even that fades with time. The black hole persists. Zoom out to the scale of a galaxy. In a large spiral, many massive stars have lived and died. Each generation of star formation produces a few massive stars for every many smaller ones. Over the age of the galaxy, countless massive stars have ended their lives in collapse. Many left neutron stars. Many left black holes with masses of a few suns. Some remain in binary systems and reveal themselves in X-rays when they feed. Others move alone, quiet, except for the slow stir they give to nearby stars and gas. Their number is large, enough that a random path through the galactic disk passes within a few light years of several. They are part of the galaxy's unseen population. The galaxy also holds a much larger black hole at its center. That one grew by different means, over long times, by swallowing gas and by merging with other black holes. It sets the scale for orbits near the galactic nucleus and influences the dynamics of the inner regions. But across the wide disk and in the thick population of old stars, the smaller, stellar mass black holes like ours make up the quiet background of compact remnants. They wait. When they meet gas, they feed. When they pass close to other compact objects, gravity waves might carry away energy and let them merge. Most of the time, they simply move through the dark. Now zoom back to the one we follow. It has settled into middle age by the clock of stars. The supernova remnant has expanded far and cooled. The hole's environment is plain interstellar gas with low density. The accretion rate is small. Magnetic turbulence still acts when gas trickles into a loose disk, but the heating is weak. The radiation is faint, possibly undetectable from far away. In such a state, the accretion flow may be hot and diffuse, with much of the energy carried inward rather than radiated. The emission spectrum shifts toward radio and hard X-rays of low brightness. The jets, if present at all, are weak and patchy. They carry little mass and little power compared to the early days. What happens to matter as it crosses the horizon in this quiet phase is the same as before. Locally, the crossing is brief and without a surface. From far away, the signals from near the horizon are stretched and dimmed. Time dilation remains an essential part of the picture. The gravitational redshift is less extreme for light emitted from radii well outside the horizon. Only the innermost regions show strong redshift and delay. Observationally, this means that the faint flow in quiet times gives less information about the exact horizon crossing, but it still follows the same rules. The black hole's rotation keeps shaping nearby space-time. Frame dragging persists. If a small disk forms with a slight tilt, the inner part will tend to align with the spin axis again. The rate at which this happens depends on the disk's density and magnetic field, but the tendency is robust. The hole's spin may slowly change over long periods if the net angular momentum of accreted gas points consistently in one direction. In sporadic feeding, random episodes can spin it up and spin it down by small amounts. Over very long times, the spin may drift toward moderate values, but in the present span, it stays close to the value set by its birth and early feeding. The quiet black hole still affects its neighborhood gravitationally. A small star that wanders near could be deflected. A cold cloud could be stirred and heated a little by turbulence in the wake of the hole's motion. These are subtle effects. The galaxy's large-scale structure dominates the motions of gas and stars. The black hole is one-point mass among many. It contributes to the gravitational field in its local region and joins the thick disk or halo population depending on its velocity. We can step again into the disk physics, now at low accretion rate. When the supply is thin, collisions in the gas are less frequent and cooling is inefficient. The flow becomes too temperature, meaning that heavier particles and lighter particles can have different average energies. The ions can be much hotter than the electrons. The electrons radiate more efficiently, so they cool faster. The ions retain heat and carry it inward. In such flows, the radiative efficiency drops. Much of the energy crosses the horizon with the gas. The luminosity falls below what a denser, cooler disk would produce at the same mass inflow rate. This is why isolated black holes can be almost invisible even when they accrete a trickle of gas. Occasionally, a denser clump passes by. The black hole's gravity focuses it slightly, and some of it becomes bound. A short, faint brightening follows as the gas circularizes, heats, and falls in. The event passes, and the hole returns to quiet. If, in the future, the black hole meets a small star and captures it into a wide orbit, there could be episodes of stronger feeding when the star loses mass. But for long stretches, nothing like that happens. The hole moves through a patch of space with low density and no close companions. We can check again the way we know such objects exist. We infer them from their effects, not from direct light. In binaries, we track the motion of the companion and weigh the unseen mass. In remnants, we map expanding shells and look for a compact source. In the galactic center, we track stars on fast orbits around an unseen massive object. In gas disks around active black holes, we see patterns of light that match the predicted temperatures and orbital speeds. In all cases, the horizon itself remains dark. The evidence rests on consistent gravitational influence and on radiation from matter just outside the point of no return. Time passes. The black hole holds its mass and spin unless it accretes. When it does, both can change. Gas that arrives with aligned angular momentum spins the hole up. Gas that arrives with opposite angular momentum spins it down. Small episodes tend to average out. Large episodes in one direction can change the spin significantly. Our black hole, with its small and sporadic meals, evolves slowly. Its horizon size remains tied to its mass, its frame dragging stays set by its spin. These define the scales for orbits and the character of any small disk that appears. In the wider galaxy, many others like it move on. Some remain near the plane of star formation. Others are kicked into higher orbits by asymmetries in their supernovae. A few pass through dense clouds and light up briefly as X-ray sources. A few find new companions and settle into long lives as accretors. Many do almost nothing but wait. They are part of the quiet structure that gravity builds and that time preserves. Our focus returns to the one we follow. It is now in its long middle age. The newborn violence has ended. The disk, if any, is thin and faint. The jets are either gone or weak. The supernova remnant has cooled and mixed with the surroundings. The whole drifts on its orbit around the galactic center, completing one turn in a span that is long in human terms and modest in stellar terms. It sometimes feeds a little. It often does not. It keeps its simple identity. A mass with a horizon, a spin that drags nearby space, a presence that you do not see, but that shapes the paths of things that come too close. Our black hole moves on its long path around the galactic center. It is quiet most of the time. It feeds a little when thin gas crosses its way. It keeps its mass and spin. Yet not all black holes remain alone. Some share space with others. Gravity brings them together when chance and history place them in the same region. The easiest way to picture this is to follow two black holes that formed in the same stellar family. Long ago, each was the remnant of a massive star that lived and died with its companion. Their supernovae did not push them too far apart. Their orbits survived, though they changed. Over time, they circle one another in a wide path. A pair like this loses energy very slowly by sending ripples through space-time. These ripples are gravitational waves. They are real waves, not in a material, but in the geometry that sets distances and times. When massive objects in a tight orbit move, they change the gravitational field around them. Those changes travel outward at the speed of light. Each wave carries a little energy. Taking that energy from the orbit makes the two black holes drift closer together. At first, the loss is small. The orbit is wide and the period is long. The waves are too faint to matter much. But as the pair spirals inward, the orbital speed rises and the rate of energy loss grows. The path tightens. The period shortens. The waves gain strength. For millions of years, the process is slow. In the last few minutes, it is fast. The frequency of the waves increases in a steady sweep. The amplitude grows. The two horizons circle each other many times in each second and then fall together. The final moments are simple in principle. There are 3 stages. First, the inspiral. This is the long period when the 2 objects orbit and slowly lose energy by sending waves into space. Second, the merger. This is the short moment when the horizons meet and a single horizon forms. Third, the ringdown. This is when the newly formed black hole settles into a smooth, steady state by sending out a last set of waves that fade like a struck bell. After that, only one horizon remains, larger than each of the originals. The mass of the final hole is slightly less than the sum of the 2 beginnings, because some mass energy left as waves. The merged hole keeps a memory of the total mass and the total angular momentum. Fine details of the 2 initial black holes are not visible in the final exterior field. This is part of the simplicity of black holes. They are defined by mass and spin. The resulting object rotates as fast as the total budget of angular momentum allows. Its horizon size reflects the new mass. Its frame dragging is set by the final spin. The space around it is smooth and steady again. We can imagine our own black hole might one day be part of such a pair. The route to this outcome is not guaranteed. The galaxy is large. Encounters are rare. Many black holes spend their whole lifetimes alone. Some live in dense star clusters, where close passages are more common. There, the gravity of many neighbors can change orbits, harden pairs, and bring objects together. Elsewhere, a black hole might drift for ages and never meet another of its kind. The story diverges with environment, but the physics of a meeting is the same whenever it happens. The system sends waves. The pair tightens. The horizons merge. One object remains. Gravitational waves move through the universe without much obstruction. They pass through matter and light with little effect. They add to the faint background of radiation that fills space. Most events are far away, so the waves that reach any one place are very weak. When they pass, they stretch and squeeze distances by a tiny fraction. The waves do not carry light. They carry information about mass and motion. They tell of tight orbits, fast spins, and sudden unions that leave a single, larger horizon. Now widen the view well beyond one galaxy. Imagine many galaxies at many distances. Black holes of stellar mass are scattered across them, as are larger black holes in their centers. Over time, some of these objects meet and merge. Each merger adds a small ripple to the sum. The background of gravitational waves builds as more pairs finish their long spirals. It becomes part of the universe's quiet radiation, alongside the faint afterglow of the early cosmos and the thin light of distant stars. Even as mergers continue in some places, the universe changes its overall character. The supply of cold gas in galaxies is consumed or heated. The rate of star formation declines. Massive stars were the first to live fast and die. They are long gone by now. Sun-like stars age more slowly. They cast off outer layers and leave behind white dwarfs. In time, those white dwarfs cool and dim. Red dwarfs live much longer than other stars, but they also have limits. They burn slowly for a span that reaches far beyond the ages we often name. Even those longest-lived stars eventually use their fuel and fade. The night sky, if one could still see it from a suitable place, would hold fewer and fewer points of light. Galaxies do not stop moving. Gravity keeps pulling on every scale. Galaxies attract one another in groups and clusters. Some merge and grow larger. Central black holes in merging galaxies may fall toward one another, and eventually combine in the manner we have described, sending strong waves across space. In the long view, structure becomes coarser. There are fewer bright knots of star formation. The universe grows quieter in visible light. Our black hole remains. It circles the center of its galaxy. It eats very little. It sometimes meets a stray cloud and glows weakly for a short time as the gas falls in and heats. It returns to faintness. It continues to store mass and spin behind its horizon. It is a simple machine of gravity, patient and persistent. The far future arrives in steady steps, not in a jump. Star formation slows and then almost stops. The remaining stars age. They become white dwarfs and cool. In time so long that language strains to hold it, those remnants are dark. They become cold, degenerate spheres that add their gravity to the quiet mass of the galaxy. Neutron stars also cool. They remain as heavy, compact objects that rarely interact. Planets that once circled stars are long gone or wander alone. The galaxy holds mostly dark remnants, thin gas, and black holes of many sizes. With stars gone, black holes become the main massive objects that change things. They drift. They sometimes capture a remnant and feed briefly. They sometimes meet each other near the centers of merged galaxies and join into larger holes. These events send new pulses of gravitational waves into space. Each event leaves a darker, heavier horizon and a smoother external field. After many such steps across many galaxies, the universe is left with even fewer distinct structures. Black holes dominate the inventory of compact mass. We can pause and describe what happens to a black hole when nothing feeds it from the outside. It does not shine by itself in ordinary light. It does not leak matter. Its mass and spin would remain unchanged if classical gravity were the only rule. But on very long timescales, quantum effects add a small process. Even in empty space, quantum fields fluctuate. Near a horizon, these fluctuations allow a black hole to lose energy slowly by radiating a faint spectrum of particles. This is called Hawking radiation. It is not light from inside. It is an effect of the horizon and quantum fields in curved space-time. The rate of this radiation is extremely small for large black holes. The larger the mass, the slower the loss. For a black hole with mass comparable to the Sun, the time to evaporate is about 10 to the 67 years. For heavier holes, the time grows very quickly. A black hole with 10 times the mass of the Sun lives roughly 1,000 times longer again. For the giant holes at the centers of galaxies, the timescale is beyond 10 to the 100 years and can be much more for the largest masses. These numbers are so large that they are difficult to hold in mind. It is enough to say that black holes outlast all stars by an immense margin. As long as the hole is massive, the spectrum of Hawking radiation is very cold. It sits at a temperature far below any current background. The universe today has a faint bath of microwave light left over from its early hot phase. That background cools as space expands. Far in the future, it will drop below the temperature of the horizon of many black holes. When that happens, the direction of net energy flow reverses. The black hole will lose energy rather than gain it from the background. The evaporation can proceed. This loss begins slowly. The mass shrinks a little, and the horizon temperature rises a little. The hotter horizon then radiates a little more. The process accelerates in a gentle feedback. For most of the time, nothing much happens. The hole simply continues to exist, giving off negligible radiation. Only near the end does the process become quick on its own terms. As the mass falls to much smaller values, the temperature climbs. The emission becomes stronger. The final moments pass swiftly compared with the earlier ages. The last instant is a brief flash of radiation, and then nothing remains. Our black hole shares this fate. It has lived through the time of stars and through the long era of dark remnants. It has perhaps merged once or twice, or perhaps not. It has drifted and waited. It has sent no messages. It has shaped the motions of objects that came within reach. Now the background is colder than its horizon temperature. The long evaporation has begun. The process takes far longer than any age we know from stars or galaxies. It continues for nearly all of what remains of cosmic time. We can zoom out to the largest scale of the story. Supermassive black holes at galactic centers endure the longest. They grew by swallowing gas and stars. They merged with one another when galaxies collided. They set the rhythm for the activity of galaxy nuclei. They used their spin and magnetic fields to launch large jets in earlier times. Now they sit in dark, quiet space with little to feed on. They are the last massive beacons of gravity. Their evaporation time spans dwarf even the long life of stellar mass holes. It can take more than 10 to the 100 years for some of them to fade. They stay while everything else cools and disperses. When even those largest holes evaporate, the universe is left with diffuse radiation and isolated particles. The background is thin. There are no stars. There are no bright disks. There are no horizons left to trap light. Space continues to expand. The fossil waves of ancient mergers pass by with amplitudes too small to affect anything. The faint glow of Hawking quanta from countless final moments adds to the background in a way that cannot be separated into events. There is no new structure being built. The story has moved past formation and growth and has arrived at dilution and quiet. Return now to the simple line that began this path. We started with a star. It lived a measured life in the way massive stars do. It fused its fuel in a clear sequence set by temperature and density. It approached an iron core and could not hold itself up. It collapsed in less than a second. It sent out a shock with help from neutrinos and shed its outer layers in a supernova. The core passed inside a boundary of no return and a black hole formed. The new horizon was smooth and silent. Spin from the star twisted space-time nearby. A disk gathered from fallback. Jets may have lit the early surroundings. The black hole then settled into a long, quiet existence. Around it, millions of black holes in the galaxy moved through their own quiet tracks. Some found companions and fed, glowing in X-rays. Some remained faint and unseen. A few met each other and merged, letting the universe ring with gentle waves of gravity. Time flowed. Stars dimmed and stopped. Remnants cooled. The sky lost its points of light. Black holes and cold objects remained. Later still, Hawking radiation began to matter. One by one, horizons gave up their mass in quanta that carried energy away. The pace quickened at the end. The last moment was brief. Each black hole ended with a faint flash and then was gone. Our one black hole was part of this long fate. It endured while stars formed and died in cycles. It outlasted the slow, bright cities of stellar light. It survived the merging of galaxies and the decline of gas. Finally, After a time that dwarfs any age we can know, it evaporated. The horizon shrank. The temperature rose. The emission climbed. The last instant came and passed. No mark remained in the dark. There is a plain lesson in this quiet ending. Gravity builds structures and holds them for long spans. Time and expansion then thin and cool the universe. Black holes, which seem the ultimate impermanence, are not beyond change. They leave a record not in stones or light, but in the fact that they keep mass and spin for almost all of time, and then release them as radiation at the end. The universe, taken as a whole, moves from hot, dense, and bright to sparse, cold, and quiet. We stand again under a night that is ours, not the far future. We remember the first fixed point you chose to watch. It looked steady. It held a simple presence in a simple sky. Inside, the core ran out of support. Collapse followed. A horizon formed. A black hole took the star's place. It lived in the galaxy for an incomprehensible span. It merged into the long flow of cosmic time. At the end, it faded like everything else.